Howdy and welcome to Chapter 4. Chapter 4 is entitled The Classical Model. Now, here's where it can get mighty theoretical and not directly useful to you, so he kind of skims over some things. He explains what the issues are, but he doesn't then go through and prove them, prove the various issues. As I mentioned, I think in an earlier video, I had taken all the econometrics classes that my PhD program had to offer. I had done all the matrix algebra and all the proofs. I've totally forgotten them. And yet, I'm still able to use econometrics in my research. So you don't need to remember all these things. There'll be a couple of things that will show up later, but then we'll emphasize them later. So I'm not going to take a lot of time on the first part of this chapter. On the second part, actually, it's kind of important. All right. So the basic idea here is, in Chapter 4, is that there are certain assumptions that must hold true, or ordinary least squares is not really a good way to estimate the relationship. And the first one is that the regression model is linear. This must be true. It's an assumption that must be true, or if it's not, then we shouldn't be using ordinary least squares. The regression model is linear, it's correctly specified, and it has an additive error term. I was trying to think here earlier which of these things, well, correctly specified, well, we hope we have correctly specified our regression. If we haven't, then we should just re-specify it. Anyway, don't worry too much about that one. The second one here has something interesting to say, though. The second one here has a practical implication. The second one is the error term has a zero population mean, all right? And let me write this up here. As I say, this one has some practical implications, so I want to spend a moment on this one. This is assumption number 2. The error term has a zero population mean. Error term has a zero population mean. All right. So, in other words, I have an example here. Let me find it. Yeah. Let's say we've got y is equal to beta sub 0 plus beta sub 1 x plus the error term. All right. Remember, this is supposed to have an average of 0. Otherwise, then this relationship here isn't really defining the phenomenon we're studying. Let's say beta sub 0 plus beta sub 1 x. Okay, so there's our regression line, all right, drawn from this right here. Let me mark that. And we're operating on the assumption that on average, that's a 0. On average, that's just kind of some random variation, right? Well, what if it's not? What if it's not random variation? What if on average, it's 3, all right? What if on average, this is the number 3? Then in that case, the actual observations of y are not defined by this on average, but they're defined by this plus 3, right? Now, why would that be true? I don't know, and I don't remember. But again, I'm going to have a practical implication here, so this is going to be worth seeing. And it's something that I don't think a lot of people who are practitioners are very careful about. But anyway, let's say that on average is 3. So really and truly, y is actually up here, 3 higher than the line. So the easy way to fix that is, how could you now make that? How could you now make that simply 0 on average? Well, just add 3 to beta sub 0. Just say, you know what? We're going to use as our intercept here rather than, down there was beta sub 0. If we go ahead and make beta sub 0 equal to beta sub 0, make the intercept, I should say, beta sub 0 plus 3, well, now that is, on average, just 0, okay? Now, don't worry too much if you didn't follow a whole lot of that, all right? Here's the bottom line. Here's the bottom line. The intercept automatically captures some of the garbage that might be there in the data. The intercept automatically fixes this problem. You don't have to do anything about this. The computer will. If on average that's actually 3 and not 0, it will automatically correct and make that beta sub 0 plus 3. You don't have to do anything. OLS will take care of it. But it means you can't trust the estimate right here. It means you cannot trust the intercept estimate. The intercept, by including an intercept, you have allowed the computer to find a way to adjust for some problems that might exist in the data, but it also makes the intercept unreliable. So, gosh, in almost all the research I've ever done, I have never bothered to say a single word about, here's my regression I estimated. I ain't said a single word about the intercept. In fact, the last paper that I did, that I've mentioned in the last video that's off at the Cambridge Journal of Economics, on my chart where I show my regression results, I didn't show the intercept. I didn't even look at it, I don't think. So it's just not important because, it's not reliable. All right, so now it's possible to tell the computer to run a regression without an intercept, which really means the intercept is 0, right? Run a regression without the intercept. That means, without specifying an intercept, that the potential problems that can be created by this not being zero on average, for example, is not being absorbed somewhere else in the model. All right? You are forcing the intercept to be 0 when you do this, and it makes this estimate now less reliable. All right? So, again, I don't even remember the math anymore now. It was 30-some years ago. But the idea is, the practical application is this: that you should place very little confidence in the estimate of the intercept. And generally speaking, you don't even bother to talk about it. And why? Because the intercept, naturally, the way the system is set up, absorbs some of the crap that may be in the rest of the data. I always think of it this way. Your family's going to come over and visit you, and your house is a mess. That one room in the house where you can put all the crap and hide it, that's the intercept. The intercept allows the rest of the house to look great. The intercept allows the other coefficients to be reliable, all right? So if you take the intercept out, it's like not having a room where you can just throw all the crap when you're tidying up the house, right? But when you have a room where you're like, I don't know what to do with this, so just throw it in that room and be sure not to let anyone into that room, that's like having an intercept, and then that allows the rest of the house to look good. So having an intercept increases the reliability of the other coefficients. Now, again, it may not have come up, but I think there's a homework problem where it implies something about the intercept. And again, remember, don't trust the intercept, but don't leave it out, because it allows the other estimates to be more reliable. Okay, so that's assumption, classical assumption number 2. Number 3. All explanatory variables should be uncorrelated with the error term. Let me write another equation up here. Put that out there. All explanatory variables should be uncorrelated with the error term. Beta sub 0 plus beta sub 1, x sub 1 plus the error term. Okay. What it's saying is that there should be no correlation between, it can still be a 0 on average, right? But there could be a relationship between this and this. And what it's saying is that if that's true, then this is going to lead to a bias in the estimate of beta sub 1. I'm trying to decide whether or not, the biggest way to fix that is to make sure it's properly specified in the first place. It is much less likely to have a relationship here unless you accidentally left something out. Because think about this. What it's saying is, this really isn't random anymore. There's some sort of pattern to it. Well, if there's a pattern, there ought to be a way to pick up on the pattern. There ought to be a way to reflect the pattern in the deterministic part of the equation, which is this part right here. If there's a pattern in this, then there is very likely a way to capture that pattern in the part that's underlined in red by perhaps including another variable. And I don't think I want to say any more about that. There's more to be said, but nothing that I think is going to be very practical to you right now. Let's see. All right, now here we do have a practical problem. This is classical assumption number 4. Observations of the error term must be uncorrelated with each other, right? So as you move from one observation of this to another, they shouldn't be correlated with each other. And that's really going to be a problem in time series. Now, a time series model is one where, like the thing I turned in, I always do time series stuff. The thing I turned into the Cambridge Journal of Economics is a time series model. I believe I mentioned in the last one that it starts in like 1953 and ends in like 2012, but it's the same country. It's the US, but across that period. That's called a time series. A cross-sectional would be, I'm only going to do 2012, but I'm going to do 50 different countries. All right, so it's one point in time, but it's across space. That's a cross-section. A time series is one, I guess, like one, not observation, one place, if you will. It doesn't have to be a place, but for me it was the United States over time, right? Now, this problem with assumption number 4 is most likely with a time series. Why would it be? Let's say this is 0, and here are your stochastic error terms. Then they should, on average, be 0, right? But there shouldn't be a pattern. For example, like that. Sometimes the error was above the line and below the line. Well, of course, it's going to be both of them. It's going to average out to 0, right? But there shouldn't be a pattern to it. And you can't really define a pattern unless it's a time series. If it's a cross-section, like, well, what would the pattern be? Alphabetical? How would I be arranging these observations down here? Down here, I'm arranging them by time, 1953 to 2012. And if there happens to be a pattern, it screws up the estimates. But there's a way to fix it. There's a way to detect this problem. There's a way to fix it. It is a later chapter. All right, so I'm just going to tell you right now that is a potential problem that we will face later, but I'm not going to talk any more about it right now because we're going to have a whole chapter on it. A whole chapter talking about how do we correct for this? If there does turn out to be a relationship among these error terms, then how can we fix that? How can we detect it, and then how can we fix it? All right, so we'll do that later. Now, what if we do have a cross-sectional study? Is there a parallel kind of problem there? And there is. Let's say we got a cross-section and we're looking at, gosh, what was that example? They were using cities, and I can't remember what the dependent variable was, but anyway. Okay, once again, on average it's going to be 0, but what if you tend to find that the range above and below 0 gets larger as you change some significant, not parameter, but like size, all right? If these are cities, small cities, and think about this, let's do, I guess, school revenue based on incomes and housing and this sort of thing, all right? Then the error term is likely to be pretty small for a small town. That how far off it was from 0 is not going to be very big because the observation itself isn't a very large number. But you get to New York City and Chicago and Los Angeles, and you've got much more variation. Right? Once again, there's a later chapter that deals with this. I'm not going to talk a lot about it right now, but it turns out to be a problem. That if there is a relationship among the error terms because along some dimension, that's what I wanted to mention, along some dimension, like size, all right? Then, now that's a little bit trickier to look for, all right, than the previous one. On the previous one, it was, is there a correlation over time? On this one, you have to figure out what that dimension is. And you could totally miss it because if you can't figure out what the dimension is, you'll never notice the problem. Again, we'll have a whole chapter on how to detect this problem and how to solve it. So that was number 5. Number 6 we just talked about. Number 6 we just talked about in chapter 3. 6 says, no explanatory variable is a perfect linear function of any of the other explanatory variables. If that is true, we have violated the assumption we can't use OLS. We can't use ordinary least squares. Remember when I was showing you last chapter with dummy variables, I said, okay, let's say that you have a dummy variable for female. In fact, let me do it this way this time. Female, male, and we'll call it DG for dummy gender. It's a dummy variable for gender. And we can define it like that. But what if you think, oh crap, I should also include one that's a 1 for male? So if you decided to include 2 dummy variables, one of which was 1 and 0 for male and female, the other of which was 0 and 1 for female and male, I think I just said the first one backwards, then the computer won't even run it. It'll say it is impossible for me to tell the difference between these 2 numbers right here, between these 2 sets of observations, that for all intents and purposes, these are the identical variable. One of them's a 1 when the other one's 0, but otherwise they're identical, and I can't tell the difference, and you're asking me, human being, to explain what's going on with this. I can't even tell the difference between these 2 variables, so it'll spit it back out. So if you have variables that are a perfect linear combination of the other variables, then they won't even run. Here's another example. What if you had batting average as one of your explanatory variables, and hits, and at-bats? Well, the problem is that batting average is hits divided by at-bats. So it wouldn't run this. It would figure out, aha, this is a perfect linear correlation here, and so it would not run the regression. All right, let's see. And we'll also talk about that in chapter 8. Let's see. And then the last one. All right. And then we get on to something I think is somewhat more substantial. The error term is normally distributed. Hypothesis testing. We're never really going to do anything directly. Well, everything that's important in discussing number 7 is actually going to be discussed here in a minute. Okay, that's the classical assumptions. You don't need to know anything else about those. And there are some homework questions, but obviously I've only emphasized those issues that I think are important. Now, the last part of this chapter brings something up that is going to be important for the rest of the semester. And that is the sampling distribution of beta hat. All right? Let's say that you want to know there's this huge barrel and it's full of blue and red marbles. And okay, it's full of blue and red marbles. I'll draw the whole thing full, but I'm not going to do it. All right, so, and then you've got a 1 cup measuring cup that you're going to use. You want to know what is the ratio of red to blue marbles in this huge barrel. What is the ratio of red to blue marbles? But you don't have time to measure, to dump them out and count them all out, right? So you're going to take a measuring cup and dip it and pull it out and use that as your sample. All right, that's the method by which you are trying to get an estimate. So you're trying to get estimates of the population. The population is the whole barrel, and what you scoop out is an estimate. Well, what we're doing in econometrics is we're basically scooping out some economic data. An important question here is our method of scooping out unbiased? Is our method of scooping out actually going to give us good samples, representative samples of what's in the barrel as a whole? Let's say that your little brother or sister is going to do it. and they're looking in the bucket. They're like, oh, the blue ones are really pretty, and they're like trying to pull out more blue. That is not going to be a good sample. That's going to be a biased sample, a sample that's biased towards blue because your little brother or sister is stupid and they don't know how econometrics works. And so they're trying to scoop out the ones that they think are really pretty. They end up with a couple of red ones in there, but mostly it's blue. And so then you do your study and you're like, well, the barrel is full of 92% blue. And in fact, that's not true because the method you used to draw a sample was biased. All right. On the other hand, let's say we blindfold a person and we walk them up to the edge and we give them the cup and they dip it in. Well, that's a pretty good, that doesn't guarantee we're going to get the right ratio. But it's a much more reliable way, all right, of getting a sample. All right, so here's the issue. We want a method of getting the sample that on average, here, let's see here. Let's say the ratio of blue to red is 50-50, all right? And then our individual estimates, that's the actual population ratio. That's what's really the ratio inside the big barrel right there. And so by dipping a cup in there, then you're getting samples, and your samples are giving you various numbers. And it's not going to get 50-50 every time, right? I mean, sometimes it's going to come out where it's 52-48, let's see what I could 60-40, whatever, right? And this way. But presumably, most of the time, you're going to get something around 50-50. Hey, maybe sometimes you might get something crazy. 90-10 or 10-90. So this is the sampling distribution. See, this is going to be figures 4.5 in the book. This is the sampling. These are the sort of samples you got when you dipped the cup in there and pulled it out, and it's not always going to be 50-50. Now, check it out. All right, so let me summarize that. That you've got this big barrel here with blue and red marbles that are 50-50. We know this from the person who put it together. But what we're going to do is just take samples and try to estimate the ratio from just those samples. So we're going to just put a measuring cup in there, and then go over and count them out and see what we got. Well, presumably, if these are randomly distributed, which is obviously a very important, what time is it? Okay, 22 minutes. A random distribution in here, then presumably we're going to get something around 50-50, but we won't get 50-50. I mean, that'll be chance that we get 50-50. All right, so, and we got to think about that with econometrics. We ran a regression, and basically we dipped a cup, all right, and we got something hopefully near what the true value is, but we'll never know, right? So what we will know, however, is whether or not we used a good method to get the marbles out. We won't know how close we are to being right, but we can control how unbiased our method of dipping in and taking out the marbles are. And so that's what we're focusing on here, is to come up with a good estimator, a good way of getting an unbiased sample. Now, the book here says something very important. It says that there are two very important properties of a sampling method, all right, of a sampling method. One of them is that it tends to center right around the true value, right? That's called unbiasedness. It's unbiased if the result of the dipping the cup in tends to get you right around the right answer, all right? On average, it gets you the right answer. That's unbiased. If it tended to go one way or the other, if it's your little brother or sister doing it and they like the blue ones, that's a biased estimator. That estimator is going to end up giving you, on average, the wrong answer because they're going to be picking out ones that they think are pretty. But if we just blindfold somebody and give them a cup measuring cup, then that should be a pretty unbiased estimator. All right, so we want it to be unbiased. We also want it to have a very small variance. Check this out. Now, I'm assuming that, well, I don't need to tell you that. Let's say we have two unbiased estimators, but one of them tends to give the distribution that's in orange and the other one in purple. Which one would you rather have? The orange one. You'd rather have one that has a very small variance. You'd rather have one that ends up being not only right on average, but right a whole heck of a lot. You know, that as opposed to, say, this really crappy estimator I have here. Oops, I should have done that a little higher, sorry. Maybe up there, right. So this one here, the green is also correct on average, but it has a very wide variance, all right? So, yeah, on average it's going to be right, but man, can you be a long way away on any individual scooping, all right? So we want one that is right on average, and it's going to be pretty close for each individual scooping. So we want it to be, let's see what we've got here. Even though, as I said, right, estimate, yep, small bias, variance can be decreased. Oh, that's a good point. That's a good point. And again, this is I'm got figure 4.5 here is showing you the whole thing about the one that's over here. That's a biased one. Notice it's ending up way far away from the true value. The other two are unbiased, but one of them has a narrower variance, which of course is what we would prefer to have. All right, so that's figure 4.5. Now, one of the points that Studentman makes here is that, hey, but the bigger sample size we can get, a bigger sample size should help us go from, even with the same measuring, well, I'm sorry, even with the same method of blindfolding somebody and having them dip a cup in, if we have that cup go from a 1 cup container to a 2 cup to a 3 cup, if we have it capture more marbles with each scoop, we're going to tend to get the orange rather than the green, which makes sense because, I mean, if we had a cup that was so large that it took every marble out of here, we'd have exactly the right answer. So the more observations you can get, the narrower the range here, the narrower the variance. So that's a good thing. It's always a good thing to have more observations. As I mentioned to you in the last video, one of the things that was disappointing about that paper I wrote was that some of the variables stopped being available after 2012 and some of them didn't start being available till 1954. I would like to have had a bigger, it was a pretty big sample size anyway, but bigger is always better with sample size. Standard error, yeah, I don't need to tell you that yet. Okay, so, and there's something called, you'll hear it said that ordinary least squares estimation is blue. Best linear unbiased estimator, right? And what that means is by best it means narrowest variance, and by unbiased it means it averages around 0. But under this conditions that are, if we meet those classical assumptions, then the ordinary least squares estimation of the slope parameters, the beta sub 1, beta sub 2, and so forth, should be blue, should be best linear unbiased. We may be way off. Even under the orange one, we could be quite a bit off, but our odds are a lot better, right? And that's it for this chapter. The only other thing I want to show you is there's a really good chart on page 108 where he sort of stops and says, okay, let's make sure you understand all of the terminology, all right? And so that's really nice, notation conventions. But just look back over that. And otherwise, dang, I'm looking forward to Chapter 5. Chapter 5, we really start getting into some actual hypothesis testing. And you know, obviously the further we go here, the more interesting it gets. But that's it for Chapter 4.